Have you ever wondered why equations hold such an essential place in physics? You see, equations are more than just mathematical expressions. They represent the fundamental language of physics, a universal tongue that transcends borders and cultures. With equations, we can describe the behavior of the physical world in precise terms. They allow us to predict the outcome of a physical event, even before it happens. Imagine being able to foresee the path a comet will take, or calculate the energy produced by a star millions of light years away. That's the power of equations. Equations are the distillation of observations, experiments, and deep thought into a compact, universally understandable form. They are the essence of science, encapsulating complex concepts in a simple, elegant manner. They're the bridge between the abstract world of thought and the tangible reality of the physical world. In essence, equations are the keys that unlock the secrets of the universe. Think about Newton's second law, F equals sine ma. It seems simple, right? But in these three little letters, there's a world of meaning, a key to understanding how objects move and interact. So let's break it down. First up, F. This stands for force, which is a push or a pull that can cause an object to accelerate. It's measured in newtons, named after the man himself. And what's a newton? It's the amount of force required to accelerate a 1 kilogram object by 1 meter per second each second. Next, we have m, which represents mass. Mass is a measure of the amount of matter in an object. It's what gives objects weight when under the influence of gravity, but it's not the same as weight. While weight can change depending on where you are in the universe, mass remains constant. It's measured in kilograms, and it tells us how much resistance an object has to changes in its motion. Now let's move on to A, the final piece of our puzzle. This is acceleration, the rate at which an object changes its velocity. Acceleration isn't just about going faster, it can also mean slowing down or changing direction. It's measured in meters per second squared. So what does F equals sine ma really mean? It's telling us that the force applied to an object is equal to the mass of that object times its acceleration. In other words, if you apply a force to an object, it will accelerate, and how much it accelerates depends on its mass. The more mass an object has, the less it will accelerate under the same force. Conversely, the less mass it has, the more it will accelerate. This fundamental relationship between force, mass, and acceleration is at the heart of Newton's second law. It's what makes a feather fall slower than a hammer on the moon, and what makes a car harder to push than a bicycle on Earth. So, Newton's second law isn't just an equation, it's a fundamental law of motion. It's a set of instructions for understanding and predicting the motions of the universe. Now let's delve into Einstein's famous equation, E = mc squared. This equation, simple in appearance but profound in implications, is a cornerstone of modern physics. Each symbol in this equation has a specific meaning. E stands for energy, the capacity to do work. M is mass, the quantity of matter an object possesses. And c stands for the speed of light, a universal constant that equals approximately 300,000 kilometers per second. The equal sign symbol is where the real magic happens. It states that energy and mass are interchangeable. They are essentially different forms of the same thing. This concept, known as the energy-mass equivalence, was revolutionary. It shattered the age-old belief that mass and energy were separate entities. So, what does E = mc squared really mean? It tells us that a small amount of mass can be converted into a large amount of energy, and vice versa. The factor of conversion is the speed of light squared, which is a huge number, signifying that even a tiny mass can yield a tremendous amount of energy. This idea has had far-reaching implications in physics. For instance, it underpins the mechanism of nuclear reactions. In a nuclear reaction, a tiny amount of mass is lost and converted into energy. This energy is what powers our sun and stars, and it's also what's harnessed in nuclear power plants and atomic bombs. Furthermore, this equation helped us understand the universe better. It allowed us to comprehend how the sun has been burning for billions of years by converting its mass into energy. It also supports the theory of the Big Bang, where a dense point of energy expanded to form all the matter in the universe. But beyond these practical applications, E = mc squared also represents a fundamental shift in our perception. It embodies the idea that the universe is a dynamic place where mass and energy are in a constant dance of transformation. So, ELMC² isn't just about energy and mass, it changed our understanding of the universe. On to the quantum world with Schrödinger's equation. Now let's delve into the realm of the tiny, the quantum world. Here, we use Schrödinger's equation, a fundamental formula in quantum mechanics. This equation might look a bit daunting at first, but don't worry, we'll break it down. At its core, Schrödinger's equation is all about waves. But not just any waves, we're talking about probability waves. These waves describe the likelihood of finding a particle in a particular state or location. The equation has two main parts. The left side of the equation represents the total energy of a particle. This includes both its kinetic energy, the energy of motion, and potential energy, the energy of position or state. On the right side, we have a fancy term called the Hamiltonian operator. This operator is a mathematical tool that helps us calculate the energy of a system. The entire equation is set in motion by the wave function, denoted by the Greek letter c. This function gives us the probability distribution for a particle. It's the secret sauce that lets us predict where a particle might be at any given time. But here's where things get really interesting. Schrödinger's equation also encapsulates the wave-particle duality of matter. This is the mind-bending concept that particles can exhibit both wave-like and particle-like properties. For example, light can behave as both a particle and a wave. It can be a stream of particles called photons, but also spread out and interfere with itself like a wave. This duality is at the heart of quantum mechanics and is beautifully captured by Schrödinger's equation. So, what does all this mean? Well, it means that the behavior of particles at the quantum level is inherently probabilistic. We can't know with certainty where a particle will be, but we can calculate the odds. In the end, Schrödinger's equation isn't just a mathematical formula. It's a window into the strange and fascinating world of quantum physics. It's a tool that helps us navigate a realm where particles can be in two places at once, and cats can be both dead and alive. So Schrödinger's equation isn't just math, it's the key to the quantum realm. As you can see, these equations aren't just symbols on a page. They are the keys to understanding the universe around us. Newton's second law, for instance, allows us to predict the motion of objects. It tells us that force equals mass times acceleration, a concept that engineers and physicists use every day. Einstein's energy-mass equivalence, the famous E equals mc², revolutionized our understanding of energy and matter. It showed us that these two seemingly different things are actually interchangeable. And then, there's Schrödinger's equation, the cornerstone of quantum mechanics. It describes how the quantum state of a physical system changes over time, giving us a glimpse into the strange and fascinating world of the very small. Each of these equations, in its own way, helps us decode the mysteries of the universe. They allow us to make predictions, solve problems, and ultimately understand the nature of reality. So remember, in physics, equations aren't just math. They are the language of the universe.